Hi everyone, we're the microplasticators and we've been working on a detection solution for the microplastics issue. Next slide, Niamh. So essentially, we looked into the microplastics problem and what it encompasses and did the by the numbers for the same. Now, microplastics are essentially particles that are less than 5 millimeters in size, and we looked at the current solutions for the same. Niamh, could you move to the next slide? Uh, yeah. Uh, so we looked at research that has been done around microplastics, and even though we know that microplastics are present a lot and ubiquitous in the environment, the effects that they have on the human and the environmental health is not completely understood. And all the mechanisms that are present for their detection right now are very expensive or time consuming. They're listed on slides. So what we wanted to do was develop a low-cost, scalable, open-source solution to this. And we looked at detection using impedance spectroscopy for the same. Niamh, could you move to the next slide? But before we get into the solution, we want to talk about how big this problem is. And for the same, yeah. So according to one 2015 some study, apparently 80 million tons of plastic that enters the ocean every year, and only 1% of it is found in the surface. That leaves, if you do the calculations, a rough estimate of around 649.8 million tons of microplastics in the oceans. You can also see some figures of rough estimates of how much plastics is present in what we consume on a day-to-day basis. And this is why, and the number sort of increases as the sensitivity of the instruments that we have increases. And so detection becomes a really crucial step in the process. And yeah, Ravi, take it.
Yeah, next slide, please. So we'll just describe, or I'll describe just the how this impedance spectroscopy works and what is the solution that's been published. This is a paper that Manu pointed out to us. So it's basically just telling you what's in the paper. So what they do is, what is impedance? Basically, it's the generalization of Ohm's law. If you put a capacitance or an inductance in the circuit, then the voltage and the current are now out of phase. And by measuring the change in the phase, you can measure properties of material. So if you introduce a plastic into a capacitor, it can change the capacitance of the instrument. Or if you put an iron particle inside a coil, you can change the inductance. So that's the idea, basic idea. Next slide, please. So here's the setup that was used by the team that published. They're using a flow-based method, and it's not clear to me because flow adds another complication here. But the key idea is it flows through a cell, which is like a capacitor, and the particles distort the capacitor or change the capacitance, and that's detected using a lock-in amplifier. Next, and the signal can be at various frequencies, and I'll just explain briefly. Yeah. So what they used is they used a set of plastic beads of different sizes, and then used comparable biological things of the same size, like brine shrimp egg, seeds of various kind, teff, various things. So basically, they want to show that they can also distinguish between plastics and biological material. Next slide, please. So here's the key component here, the lock-in amplifier. How does it work? It's a very simple idea. So you take the product of the input signal and the signal that comes after it passes through the capacitor. So you introduce a phase shift, and it uses a very simple trigonometric relationship. It's if you multiply two cosines, cosine A and cosine B, it can be decomposed as cosine of A plus B and cosine of A minus B. And now if the two frequencies are close, if A and B are only separated by a phase angle phi, then you get two components, one which is twice the frequency and another which is only the phase angle. So, and then if you apply a low pass filter, you remove anything that has a frequency component, and you end up reading purely the phase change. And this becomes very, very sensitive because even with a very noisy signal, you can extract this phase change, and you can actually, and apparently can go down to 1 part in a million sensitivity. Next slide, please. So here's how it looks. So what they claim, just to quickly summarize what's in here, the key claim they're making is at both 1.1 megahertz and 10 kilohertz, the phase change is negative for biological samples and positive for plastics. So that's a key takeaway message here. Next slide, please. Yeah, go ahead.
Okay. Can you hear me?
Yeah.
Oh, you can.
Yeah.
Okay, good. So we need a couple of things to do this for our prototype. We want to make it as low cost and simple as possible. So we need a signal generator. So we can use a 555 signal generator, which is just like a little chip that's maybe 50 cents. It's really cheap. So we could try one of those, or use a tone generator and a headphone jack, which I'll explain more about in a minute. Then we need a capacitor. So in the paper that we just talked about, they used copper PCB plates as the capacitor. I couldn't actually get my hands on those, so we just used tin foil instead, or aluminium foil. And then for the detection, we need to use an oscilloscope. So then for our initial test, we wanted to test kind of air, so with nothing in it, tap water, and microplastics, brine shrimp eggs. And then we wanted to try it out on milk to look and see if we could detect microplastics in milk, because that's something that, you know, is consumed widely. Also a sample that we could kind of all access from all our different parts where we're around the world where we're living, that we could all test. So we were like thinking that milk might be a good idea, and also maybe to look for microbes in milk, to look at milk spoilage potentially as an idea. And then at the end, we wanted to simplify our idea, miniaturize it, and kind of make it scalable. Then, so we came up with the idea of, Ravi was looking at the idea of looking at using your laptop as an oscilloscope. So he found a video that kind of shows you how to do that. And I was looking at using the laptop as the tone generator, as the signal generator. So you can do that by playing different tones of different frequencies, and then using a headphone jack, splitting out the cables from that and taking those frequencies and putting it into the oscilloscope. And then for detection, we ended up using an oscilloscope that we have in the lab. So we could look at the signal we put in, and then the signal that comes out after passing through our sample, and look at the kind of the waveform of both. So our first step was to use the tone generator. So there's the headphone jack attached into the oscilloscope. So we kind of soldered wires onto the headphone jack to the ground and the positive pin there. And you can see when you change the frequency, we can see a change in the oscilloscope. We also tried generating signals with a red Pataya board and the 555 module. Couldn't get the red Pataya board working, but the 555 module gave us nice square waves. So there's a potential to turn those square waves into sine waves later on if we want to. Then we add our Frugal capacitor. So this is just tin foil on two acrylic plates. And we measure the voltage across the headphone jack, the positive and negative of the headphone jack. And then we also have a channel into the oscilloscope across the second resistor there after the tin foil. We played with resistors, adding different resistors to see what the effect on the waveforms were. And we saw we could kind of decrease some of the noise. But really, if we want to get rid of those noisy signals, we need the low pass filter on the lock-in amplifier. Then we tried measuring phase changes at multiple frequencies. We found we got, with no sample there, we got a roughly twofold change for a twofold change in frequency. But what we said was we needed a higher capacitance. So we needed to basically bring those plates closer together to get better readings. So our little tube there, we needed to replace that with a smaller cuvette. So we got a smaller cuvette to move the plates closer together, and we tested it with air, water, and microplastics. We didn't get a chance to do brine shrimp eggs or milk, but we saw a phase change of 0 degrees for all samples when we worked it out. But we think what this is that our capacitor needs to be smaller or larger relative to the size of the cuvette, so that it's kind of the cuvette and the water or your sample is taking up all of the space. I'll pass over to Ravi.
So next slide, please. So we just want to quickly, okay, so here's another by the numbers. So we actually did some rough calculations of what happens if you, how much effect. So the dielectric constant of water is 80. The bead is 2. So basically putting beads in is reducing the capacitance. And we can estimate that having one bead at a size of 2 millimeter cube, let's say, would be about 1,000. Oh, yeah, 1,000. So we can detect these capacitive changes if you had a lock-in amplifier, or if you had more beads. So one of the two, and so it is detectable, at least roughly, by playing with these numbers. Next slide, please. So the idea is that we can eventually, maybe if we can distinguish live bacteria from plastics and things like that, then you can actually use it even for looking at cultures and looking at numbers of bacteria. So you can look at milk and beer things. So the key things to be done are like use the 555 based amplifier, so oscillator, so it can be a miniature generator, set up the lock-in amplifier, deal with the capacitance to package it nicely, and then just tune the resistors and frequencies to see which one works best, and then that's it. That's our idea of how we're going to go forward.
So that was fantastic, team. You guys set a pretty high bar for everybody. I don't know if we have time for questions. One question, just a side comment. I think the capacitor really has to be small.
Yeah.
Because what you want to do is the ratio of your volume
Yeah.
of the capacitor to the plastic volume is what you want to bring down.
Yeah.
And there's also this thing called fringe fields. When the two capacitors come, there are fields on the sideline which are not seeing the volume that you care about. So,
Right.
but we'll talk offline.
Yeah.
I mean, I have to say, I am thrilled since the last chat. This is,
Thanks.
it's got real legs. But any questions anybody has? Yes, Tanvi.
Are there frugal versions of the oscilloscope? Like,
Yeah. That's so the laptop. So the oscilloscope is only for matter of testing in the beginning, because eventually the lock-in amplifier will give you a readouts, which is just basically reading out the phase change. And actually, if you look at like how reagents are supplied, for example, if you look, Illumina will send you something, they have a small detector that actually records the temperature every 5 minutes. It's like a really small thing. So you could have something like that, which will record the phase changes as we add, and then you can then download it to a laptop or something later on, or a phone, and get the numbers.
I think eventually you don't need an oscilloscope. That's just a debugging tool.
Yeah. But that can be done
The math
cheap.
of this is so simple that couple of cents of electronics is all you need to actually implement. I think the lock-in amplifier is the tricky part.
Yeah, I looked up. You can do it.
There are a couple of tricks to implementing something like that. But, you know, analog electronics, it really scales.
Yeah. And there's a chip that Texas Instrument makes. I looked it up. You can get it, and it's only like 50 cents again. So it's really cheap to put this together.
Yeah. Okay, to be continued.